Here is the rewritten script, maintaining 100% of the original content, logic, and length, while following your formatting requirements. Pull up a tomato plant at the end of summer that has been fed all season with one simple kitchen ingredient, and the root ball will not look like it belongs to the same plant. It will be dense, fibrous, and 2 to 3 times the size of the same variety grown without it. That is not garden folklore. The effect has been documented in peer-reviewed agricultural research published in the journal Crop Science. And the ingredient itself costs less than $1. It sits in nearly every pantry in America. It is so common that most gardeners walk right past it on the kitchen shelf, never knowing what it can do under the soil. This is the story of why that $1 packet is not on the shelf of a single major garden center in the country. Not because it is illegal, and not because of any kind of conspiracy. The reason is far simpler, far stranger, and rooted in basic biology. And once it makes sense, it explains why every serious home gardener over the age of 55 ought to know how to use it. For most of a gardener's life, the eye is trained upward, up at the leaves, up at the blossoms, up at the fruit. When a plant looks tired, the first thought is to spray something on the leaves. When fruit refuses to swell, the first thought is to scatter fertilizer on the surface. When a transplant wilts, the first thought is to give it more water and hope for the best. But the truth that takes a lifetime in the garden to fully understand is that everything a plant becomes is decided in the dark. If the roots are shallow, no amount of liquid fertilizer poured on top will fix the harvest. If the roots are thin and stringy, the plant will collapse the first time a heat wave settles over the garden in August. If the roots are starved of oxygen, water, or microbial partners, the leaves above the soil will yellow no matter how much nitrogen is sprayed. This is the quiet rule that almost every modern garden product seems to ignore. The garden center aisle is built upward. Leaf sprays, bloom boosters, fruit setters, and foliar feeds. These are profitable, colorful, easy to bottle, and easy to stock. But the engine of the plant, the only thing that ultimately decides how big a pepper will swell or how heavy a tomato will hang, lives entirely below the soil line, 12 inches under the dirt. That is the place this video is about. Not the leaves, not the blossoms, but the root. So, the question worth asking is this: what does a root actually need in order to triple in size and density? And why is the answer to that question not sitting in a tub on a store shelf, where anyone over 55 could walk in and buy it? Walk through the aisles of any major garden store this spring, and the rooting hormone shelf tells a curious story. You will see small plastic tubs of powder, most of them priced between $5 and $15. The premium brands climb toward $30 for just a few ounces. The active ingredient on the label is almost always the same: indole 3-butyric acid, sometimes paired with naphthalene acetic acid. These are synthetic auxins, laboratory-made copies of the very hormone that plants naturally use to push out new roots. These products are not a scam. They genuinely work. But they are synthetic imitations of something a living organism produces for free. Here is the question almost nobody at the garden store ever thinks to ask. If a single-celled fungus, already in nearly every American kitchen, produces the exact same rooting hormones and produces them in living form surrounded by amino acids, B vitamins, and trace minerals, why is that fungus not for sale on the same shelf? The answer is not corporate suppression. The answer is physics and shelf life. The moment that fungus is awakened in warm water, it begins releasing carbon dioxide gas at a rate that builds pressure inside any sealed container. Within 48 hours, a plastic bottle of this living solution would bulge, lean, leak, or burst on a warm shelf in a Texas warehouse. There is no preservative that can lock the organism into a 6-month shelf life without killing the very thing that makes the product useful. Bottled rooting products have to be dead and stable. This one has to be alive and active. That single physical fact is the entire reason it cannot sit on a retail shelf. Combined with a profit margin of essentially zero, there is no commercial reason for a major brand to ever try. So, the recipe lives where it has always lived, in the kitchen, made fresh in about 30 minutes from start to finish. The fungus is plain dry baker's yeast. The scientific name is Saccharomyces cerevisiae, and what it does to a root system is unlike anything else a home gardener can buy. Generations of grandmothers have used Saccharomyces cerevisiae for exactly one purpose: to make bread rise. But peer-reviewed research published in Crop Science in 2014, in the journal Plants in 2023, and in Frontiers in Industrial Microbiology in 2024 has quietly documented a second, far more interesting purpose for the same powder. When living yeast cells are introduced to soil at the root zone, 3 things happen at the same time. The first is hormone signaling. Saccharomyces cerevisiae produces indole-3-acetic acid, abbreviated IAA. This is the master signaling molecule of the entire plant kingdom. It is the chemical message that tells a root cell to divide, to stretch, and to push out a new root tip. It is the same hormone class that synthetic rooting powders try to copy in a laboratory. The yeast also produces cytokinins, a second hormone class that signals cells at the tip of every root to multiply faster, which is where new lateral branches form. The 2024 Frontiers paper measured significantly higher chlorophyll levels in lettuce seedlings treated with brewer's yeast and attributed those gains directly to the auxin and cytokinin produced by the living fungus. The second is a microbial feast. As the yeast cells multiply in warm sugar water, they release amino acids, peptides, B vitamins, and trace minerals, nitrogen, phosphorus, potassium, magnesium, iron, zinc, and several others, directly into the surrounding solution. These are not raw, locked-up minerals that the plant must spend energy breaking down. They are already in the pre-digested forms that root hairs can absorb almost on contact. It is the closest thing in nature to a direct intravenous feed for a stressed plant. The third is colonization. The yeast cells settle into the root zone and physically occupy space. They compete with soil-borne fungi for nutrients. Studies on lettuce and tomato have noted lower incidence of certain damping-off pathogens when yeast is present in the root zone, attributed partly to that simple space competition and partly to antimicrobial peptides yeast secretes as it grows. 3 effects from 1 teaspoon of pantry yeast: hormone signal, nutrient feast, and microbial defense. And there is one more piece of this story, the strangest piece, the piece that genuinely surprised plant scientists when it was first observed under a microscope in 2010. For most of agricultural history, roots were considered passive, like straws sipping dissolved minerals from damp earth. That was the textbook picture, and it stood for over a century. Then, in 2010, Dr. Chanyarat Pongkun-Lonhayen and her research team at the University of Queensland in Australia used confocal laser scanning microscopy, a kind of fluorescent imaging that can see inside living root cells in real time, to watch what actually happens when living yeast cells meet a young tomato root. What they observed was so unexpected they had to give it a brand new name in the agricultural literature. The roots were not sipping, the roots were eating. The root tip cells engulfed the living yeast cells and pulled them inside into the space between the cell wall and the cell membrane. Once inside, the plant cell produced a controlled burst of superoxide, a mild oxidative pulse that stripped the cell wall from the yeast and made the internal contents of the fungus available for absorption. Nitrogen, phosphorus, stored proteins, everything the yeast had built up while feeding on sugar in the warm water. Then something even stranger happened. Some yeast cells survived this process. They emerged out through the lengthening root hairs, rebuilt their walls back in the soil, gathered new nutrients from the surrounding earth, and were eventually consumed again. This process was named the rhizophagy cycle. The word means root eating. Since 2010, dozens of follow-up studies in monocot and dicot species have confirmed the cycle. The 2014 paper from the same Queensland team, published in Crop Science, demonstrated the same uptake in sugarcane and tomato roots using both living and heat-killed yeast. In practical terms, for a vegetable gardener over the age of 55, this means something quite specific. A tomato root is not just a drinking straw. It is an active harvester that pulls live microorganisms inside its own tissue and extracts nutrients directly from them. Yeast happens to be one of the few microorganisms common enough, safe enough, and cheap enough that a home gardener can supply it deliberately every season for less than $1. The plant does the rest of the work on its own. A short, honest look at the numbers is worth the time, because gardening videos online tend to inflate the math. The truth is more measured and more interesting because of it. In the original 2014 Lonhien study published in Crop Science, both living and heat-killed Saccharomyces cerevisiae were added to fertilized soil planted with tomato and young sugarcane. After 10 weeks for sugarcane and 4 weeks for tomato, root biomass was significantly higher in the yeast-treated plants. Nitrogen and phosphorus content in the roots and shoots was substantially elevated. The root-to-shoot ratio increased in both species, which is exactly what a gardener wants, proportionally more underground engine for the same plant. A 2023 study published in the journal Plants tested auxin-producing yeasts isolated from Mexican maize landraces. The 4 most promising strains, when used as soil inoculants, produced a 1.5-fold increase in plant height, fresh weight, and root length compared to untreated control plants. Not synthetic chemistry, just living yeast inoculated into the root zone of a corn plant. A 2024 Frontiers in Industrial Microbiology paper using residual brewer's yeast on lettuce and tomato seedlings reported measurable improvements in seed germination, leaf number, fresh weight, and chlorophyll content at a yeast concentration of about 10 million cells per milliliter. These are not miracle numbers. They are real numbers from real labs. A noticeably bigger root mass, higher mineral content, and better transplant survival. Real measurements behind a $1 packet of pantry yeast. And here is the part where home gardener observation often outruns lab measurement. In a controlled 4-week tomato trial, root biomass gains plateaued within the trial window. In a full 8-month season, a real backyard garden with 3 strategically timed applications, the difference between a yeast-fed tomato plant and an untreated one is most dramatic at the end of the season when both plants are pulled out. The yeast-fed root ball is often 2 to 3 times denser, with visibly more lateral branching. That is the experience that gives this recipe its long reputation. The lab confirms the mechanism. The garden confirms the scale. Now, the recipe itself. It requires 3 ingredients: 1 liter of non-chlorinated water, 2 tablespoons of plain dry baker's yeast, which is roughly 20 grams or 2 standard packets, and 1 tablespoon of plain white sugar. Any pantry, any town, any season. Total cost, depending on the brand of yeast, is somewhere between 60 cents and $1. Step 1 is temperature, and this is the step where most home attempts quietly fail before they start. The water has to be lukewarm. The accepted range for activating dry yeast is between 105 degrees and 115 Fahrenheit. Bob's Red Mill and Fleischmann's both publish the same range. The simplest test for anyone without a thermometer is to touch the side of the jar with the back of the wrist. The water should feel comfortable, slightly warm, not hot enough to flinch from. If steam is visible rising from the surface, the water is too hot, and the yeast will die on contact. If the water feels cool, the yeast will stay dormant, and the brew will fail. A reliable cheat for cooler kitchens. Boil a full kettle, pour the boiling water into a clean glass jar, and let it sit on the counter for 15 minutes. The temperature will drop into the safe range on its own. Step 2 is dissolving. Use a glass jar of at least 1.5 liters in capacity. Pour the warm water in, add the 2 tablespoons of yeast and the 1 tablespoon of sugar. Stir gently with a clean spoon until everything dissolves into a slightly cloudy beige solution. A quick word about the sugar because it gets misunderstood often. Plant roots have no use for refined sugar. The sugar is not being added for the plant. The sugar is the wake-up signal for the yeast. Without it, dry baker's yeast stays in deep dormancy and produces almost no hormones, no amino acids, and no biostimulant value. The sugar is consumed almost entirely by the fungus during the next 30 minutes. By the time the brew is applied to the garden, the sugar is gone. Step 3 is covering. Do not seal the jar with a tight lid. As the yeast wakes up, it produces carbon dioxide gas. A sealed glass jar can crack within hours from the pressure. Instead, lay a clean paper towel across the opening and hold it in place with a rubber band. The gas escapes safely, while dust and insects stay out. The jar also needs to sit in the dark. Direct sunlight delivers ultraviolet rays that damage yeast cells before they finish their work. A closed pantry shelf, a kitchen cabinet, or even a dark corner of the counter under a folded dish towel works perfectly. Step 4 is waiting 30 to 40 minutes. During this time, the yeast is rapidly multiplying, consuming the sugar, and releasing hormones, amino acids, and B vitamins into the surrounding water. The visible signs that the brew is ready are a foamy beige cap forming across the surface, and a steady stream of tiny bubbles rising through the liquid. The smell is mild and slightly bread-like, familiar to anyone who has ever proofed yeast for a loaf of bread on a Sunday morning. When the foam appears, the concentrate is alive and ready. One final step before any of it touches a plant: dilution, timing, and where to pour. The concentrate is too strong to apply directly. Used at full strength, the yeast population is dense enough to briefly disrupt the existing soil microbiome and stress fine young root hairs through sudden osmotic pressure. Dilution is not optional. The ratio is 1 to 10. Stir the 1 liter of brewed yeast solution into 10 liters of plain, non-chlorinated water. Rainwater collected in a clean barrel works beautifully. Tap water that has been left to sit uncovered in a bucket for 24 hours, allowing chlorine to evaporate, works just as well. The result is 11 liters of finished, ready-to-use biostimulant. Apply to the soil, not the leaves. The hormones and amino acids in this mixture are designed to work at the root surface, not on foliage. Pour the diluted solution slowly at the base of each plant, soaking the soil thoroughly to a depth of about 6 inches without flooding. For a mature tomato or pepper plant, roughly 1 liter of the diluted mix is sufficient. For seedlings or fresh transplants, a single cup is enough. Timing is what separates a casual home trial from a transformative one. This mixture is not a weekly fertilizer. It is a strategic biostimulant designed to hit 3 specific moments in a plant's life when root growth matters most. The first application is a transplant. The moment a young seedling moves from a starter pot into open garden soil, it enters a brief period of stress. The flood of yeast-produced auxins delivered to the root zone at this exact moment supports rapid lateral root expansion and noticeably reduces transplant wilt. Plants treated at transplant tend to hold their leaves firm through afternoon heat within the first week, instead of drooping. The second application is at the very first sign of flowering. This is the moment when the plant decides how much energy it can commit to fruit production. A strong, expanded root system at this stage means more flowers held, fewer dropped, and better pollination outcomes. The third application is when the first small fruits appear. The plant now needs to pull in heavy nutrient loads to swell each fruit to full size. A second wave of yeast-supplied amino acids and minerals at this stage supports the demand without forcing the plant to compete with itself. 3 applications spaced across the season. That is the entire system. More frequent applications risk shifting the soil microbial balance too far in one direction. Less than 3 misses the windows when it would have made the difference. A word about expectations, because this is where most online gardening videos lose credibility. A single application of yeast water will not transform a struggling plant overnight. The visible changes show up gradually. Within the first week after a transplant application, the plant tends to hold its leaves more firmly through the heat of the afternoon. Within 2 to 3 weeks, the new lateral roots have established and the main stems visibly thicken. By the end of the growing season, the difference between a yeast-treated tomato and an untreated one shows up most clearly not in the fruit on top, but in the root ball below. Pulling a yeast-fed tomato or pepper at the end of the season often reveals a root mass 2 to 3 times denser and more fibrous than an untreated plant of the same variety. A few practical mistakes can quietly ruin the brew. Water hotter than 120 degrees kills the yeast before it activates. The brew will smell sour rather than bread-like. If that happens, pour it out and start over with cool, fresh water. A tightly sealed lid is the second common mistake. Carbon dioxide pressure builds quickly, and glass jars can crack without warning. A paper towel cover is the solution. Old yeast is the third mistake. A packet more than 2 years past its date may no longer activate. If nothing happens within 40 minutes, the yeast is dead. Storage is the fourth mistake. The diluted solution does not keep. Use it within 24 hours of mixing, or the yeast population crashes and fermentation tips toward alcohol. Application during the hottest part of the day is the fifth mistake. Pour the solution in the early morning or late evening when soil temperatures are moderate. The strongest results show up in heavy-feeding vegetables like tomatoes, peppers, eggplant, cucumber, zucchini, and corn. Strawberries respond well during the runner stage. Leafy greens show gains during the seedling and transplant phase. Root crops benefit primarily when applied during the early establishment window. Established perennials and fruit trees respond more slowly, but show improvement in new feeder root density when treated in early spring. There is something quietly satisfying about a garden recipe that comes from the back of the pantry instead of a plastic jug. The same yeast that has made bread rise in farm kitchens for generations also makes a root system reach deeper and branch wider. The earth has been generous with its tools all along, and the most useful one was sitting on the kitchen shelf the whole time. If this story changed the way you look at the simple ingredients in your pantry, please subscribe and like the channel. We are uncovering the natural history and biological secrets that have been hidden in plain sight. Let's grow a better future together. Our next garden treasure will be revealed very soon.